This is problem 4-92E. It's on page 204. In a production facility, 1.2 inch thick, 2 foot by 2 foot square brass plates with given properties there that are initially at a uniform temperature of 75 degrees Fahrenheit are heated by passing them through an oven at 1300 degrees Fahrenheit at a rate of 300 per minute. If the plates remain in the oven until their average temperature rises to 1000 degrees Fahrenheit, determine the rate of heat transfer to the plates in the furnace. Okay. Let's write down what's given. So here's the plate, and here's a plate. 2 foot by 2 foot, thickness 1.2 inches, initial temperature 75 degrees Fahrenheit. After going through the furnace, the temperature should be 1000 degrees Fahrenheit. Okay. The flow rate is 300 plates per minute. Now, the property data that was given was that the density of the brass is 532.5 pound mass per cubic feet. The heat capacity is 0.091 BTU per pound mass per degree Fahrenheit. Of course, if you want to write all this down, you're welcome to, but I always post the example problems in Blackboard. Right now, there's just one. Like I said, when I figure out one for boundary work, I'll add it to the example PDF. So you can have a copy of the sheet I'm working from if you want. The temperature far away, the temperature of the furnace was given as, is that 12 or 13? Let's see, it looks like it's 1300 degrees. Okay, so the temperature far away, and remember we called that T infinity in 220 for heat transfer. So the temperature of the furnace is that much, and we're supposed to find the heat transfer rate. Okay, well, the heat transfer rate is a big Q dot, right? So large Q is talking about total amount of heat transfer. The dot makes it a rate. Okay, well, we can calculate it as the mass flow rate of plates through the system multiplied by the specific heat transfer. In other words, if we know how much energy we have to add to each pound of brass, right? This is energy per pound, and how many pounds per time are going through, that would tell us the heat flow rate. Does that make sense? So this is how we're going to approach the problem. Well, how can we quantify the mass flow rate? Well, I've got a flow rate here already in plates per minute, so it'll have to be something with that, right? So if I've got plates per minute, I'd like to know how many pounds per plate there is, right? So I could use the density times volume to talk about how much mass there is. Let's think about the units to make this clear. And all I'm doing right now is working with the mass flow rate. So this is mass per volume times volume of the plate. So you see how we're just getting mass out of this, right? So and this would be the mass per plate, really, because that will be my basis. See how all the units work out then? So unit of plates and volume go away. We'll just have mass per time. Okay, so I have to make sure that's the volume per plate, but that's pretty easy because the plates are 2 foot by 2 foot by 1.2 inches. Okay. In fact, if you calculate that volume, I already did that. The volume turns out to be 0.4 cubic feet per plate. I won't go through the details. You guys know how to do that. That's pretty straightforward. Okay. So that takes care of the volume. The density was given, and we know the flow rate. So this bit here represents the mass flow rate. How about Q? Well, what could we do with Q? What is Q? Well, Q represents the amount of energy you have to add to the plate to get it to change its temperature, right? Does this sound like heat capacity? Well, it's related. You have to be careful. Heat capacity, if we look at the units, I'll just go ahead and write it out. Q equals Cp delta T is what we use. Think about it though, the units of heat capacity are, or the dimensions are, energy per mass, per temperature, right? And this is specific heat capacity because it's per unit mass. So it's how much energy you have to add per each unit of mass to change its temperature. Then if we multiply that by the temperature, then we just have energy per mass, which is what we want. You see how Q is Cp delta T? So let's plug that in. So Cp delta T is the way we're going to expand and solve for Q.
That's the same for, you could just put little u there, right? The internal energy.
Could we put internal energy? Yes, we could. You're exactly right. We could put delta U there. Yep. Good observation. Anything else?
There's a lot of Q's up there, so.
There are a lot of Q's. Yep, you're right. So we could have used, I'm using Q because it's heat transfer per mass, but you're right, you could talk about the energy change per unit mass, because that's what the heat's going to do, right? The heat's going to go into the brass. It's not going to remain heat. It can't be, right? The brass is the system. It's going to change the internal energy of the system. Okay. Good job. Good observation. All right, so now we should be able to calculate this, because I think we have everything we need, right? The flow rate is 300, and let's write the units below, otherwise I'll run out of space. Plates per minute. The density is 532 and a half. May run out of space anyway. And that is pound mass per cubic foot. The volume is 0.4 cubic feet per plate. So see how plates go away? We've already discovered this, right? So far we have pounds mass per minute. And then we need the heat capacity, but that was given as 0.091 BTUs per pound mass per degree Fahrenheit. So pound mass go away. We have BTUs per minute per degree Fahrenheit. Times, now the change in temperature, well, that's 925 degrees. Do you guys see how the delta T is 925? We got to go to 1,000 from 75. So 925 delta degrees Fahrenheit, if you will. And so this is just degrees Fahrenheit. That goes away when we have BTUs per minute, which is what we were looking for. Okay. Plugging all of this into your calculator, you'll find it's only 5.378 times 10 to the 6th BTUs per minute. Now, if you had a feel for BTUs or a minute, you'd say, only? Really? This is absolutely huge. Let's convert it to kilowatts, because you might have a bit of a feel for kilowatts because you pay your electric bill, right? Or at least you're hopefully somewhat familiar with. My electric bill runs anywhere from about $100 to $200 a month, depending on how much I run my AC. Okay? So for that, it turns out electricity costs about, very roughly, 10 cents a kilowatt hour. It's actually a little higher than that now, but that's good enough for our back of the envelope calculation. So let's say I pay $150 for electricity for my house. Okay? At 10 cents a kilowatt hour, that means I bought 1,500 kilowatt hours. Does that make sense? So 1,500 kilowatt hours of energy. Well, what is a kilowatt hour? Well, it's the amount of energy you use by letting electricity flow at a rate of 1,500 watts for 1 hour. Okay? Now, obviously, I never let 1,500 watts flow. What do you think? No, I'm sorry, 1,500 kilowatts. That would be 1.5 megawatts. My house never pulls 1.5 megawatts at a time, okay? Serious things would burn if that happened, okay? But you see how I went to kilowatts, right? Okay, so 1,500 kilowatts for 1 hour would be quite a power flow rate. Well, it turns out this Q dot, if you convert this to kilowatts, it's 94,568 kilowatts, okay? Let's compute the cost of letting this much energy flow for a whole month. Okay. All right. As if we're buying that energy in the form of electricity. Let's just assume that and see what it costs. And for the sake of our calculations, let's make it easy on ourselves and make it 95,000 kilowatts. What's a few kilowatts between friends, right? Okay. So let's make it 95. So punch 95,000 kilowatts into your calculator. And let's say that we're just producing for 8 hours a day, all right? Average month, let's take it to be 30 days. So 8 times 30 would represent the number of hours that we let this system run in a month, right? So multiply 95,000 times 8 times 30. What do you get?
Almost 23 million.
Okay, now Fortunately, electricity only costs about 10 cents per kilowatt hour, so divide that by 10 or multiply by 0.1. How much money are we talking about?
2.3 million
Is that all per month?
per month.
Oh, well, we can run 2 of these factories at that price, right? Do you get the idea that this is a huge power flow? Okay, in fact, you remember the Griswolds when he put all the lights on the house and plugged it together and they had to turn on the auxiliary nuclear reactor, okay? Power plants don't start up that quickly, by the way. But anyway, okay, this, let's see, the turbines on the river produce what? 10 megawatts apiece, something like that? Okay. This is 100 megawatts. This is the capacity of the plant on the river. Okay, that's how much we're sucking up here. You think that's going to draw a little bit of power from the power company? Oh, yeah. Yeah, I'm just rounding everything off. They're upgrading their capacity. Each one is about 10 megawatts as they set, and they were upgrading them to 12, 13, and times they ended up being in the neighborhood of 100 megawatts. So we're using all of the power company on the river to do this. So.
I'd love to see the wires between you and them. you
Right,
know,
yeah.
all that.
Well, as long as they're really high voltage, it wouldn't
Yeah.
have to be all that large, but it'd still be impressive. Do you get the idea that this is probably not a good way to do this? Okay. If you actually had to heat up the brass that much and you had that kind of flow rate, you'd probably fire this with gas or some other energy form that's a lot cheaper. Because think about what's going on here. We're using thermal energy, right? Wouldn't it be best to take the chemical energy and convert it directly into thermal? Now, if you're using something like the river flow, well then, that's just work already, right? That's mechanical energy being converted to electrical energy. But for something like this, I'd much rather burn fuel. Okay. Any questions, comments?
You could use the river to bend the metal back and forth by sticking it in.
All right.